Thank you so much. Can everyone hear me and see my screen?
Yes, we can see your screen and we can hear you.
Okay, great. So my name is Achal Gupta, and I'm going to be talking a bit about black holes and white holes today, and also about the crazy math that's involved with them. Um, so before we get started with the black hole side of things, I want us to establish sort of common ground so that we have the tools we need to be able to understand black holes in a new light. So firstly, we'll define what space-time is. So our intuitive understanding of the universe is built on three spatial dimensions, and that's forward, backward, upwards, downwards, to the left and to the right. But that's not a complete definition of a point in space-time, because if I wanted to meet someone, for instance, I wouldn't give them the address of a restaurant only. I'd also tell them what time I'm meeting them. Therefore, what the argument being made here is that time and space are interwoven, and they form a 4D continuum called space-time. And this is also according to Einstein, that time is not a separate universal parameter that ticks at the same rate for everyone. Um, so a point in space-time is called an event, and you need 4 coordinates to describe it. That would be your x, y, z, and then your time t coordinates. So obviously the human mind cannot comprehend a 4D continuum, so we use a conceptual tool called a space-time diagram. So we're going to be using a very simple form of a space-time diagram known as a Minkowski diagram. This is basically compressing all 3 spatial dimensions onto a single representative spatial axis. So our x-axis here represents all of space, up, down, forward, back, left, and right. And then what we do is we make our perpendicular axis the time axis. So now this represents time. And now what we do is we modify this time axis by multiplying it by the one universal constant in this universe, and that obviously is the speed of light, 3 times 10 to the 8 meters per second. So by multiplying this constant, the speed of light, to our time axis, what we've effectively done is brought our time axis and our space axis to the same units, and this lets us utilize the space-time diagram for its interesting properties. What do I mean by that? Well, firstly, now any path for any object in space-time, whether they're stationary or moving, is no longer a single point on this diagram. It's always going to be a line, and it's always going to be a continuous line. So this continuous line is a world line, and a world line, we can have a few different types of world lines. You can see this yellow world line is just an arbitrary world line that I've drawn in the space-time diagram. We can also have a perfectly vertical world line, and what a perfectly vertical world line represents is an object that's stationary in space, but is obviously moving through time. So they would have a perfectly vertical world line because the space coordinates not changing as time progresses. We can also have a diagonal world line, and a diagonal world line is simply us moving at a constant speed through space because we're covering a given distance in space in a given amount of time. And this gradient, the gradient of this world line will indicate the speed that we have relative to the speed of light. Because remember, we multiplied our time axis by the speed of light. Therefore, any gradient will be giving us a speed relative to the speed of light. We can also have a perfectly horizontal world line. And what this represents is traveling an infinite or a given amount of distance in 0 time, which signals infinite speed and therefore is impossible for us to do. So you'll notice that we've talked about vertical world lines where we're moving at no speed, but we've talked about horizontal world lines which are moving at infinite speed. And we mentioned that we cannot cross the speed of light as matter. No matter can cross the speed of light. What this means is we have a critical line at the slope of 1, simply because of our speed of light, and this represents the world line of any photon moving through space-time, because it's covering the same distance every single time, and it's covering it at the speed of light. Most importantly, in the space-time diagram, this line will have a slope of exactly 1, and lines like these, world lines like these, are called light-like world lines because they're moving similar to how a photon would move through space-time. And any line steeper than this, aka a line that's fairly closer to the vertical world line, is called a time-like world line because you're moving slower than the speed of light. And any line shallower than this is called the space-like world line, because you're moving faster than the speed of light, and that's obviously impossible. So now what we're going to do is we're going to take another light-like world line, this time moving in the opposite direction, and we're going to have it cut through the origin of this space-time diagram. Now what we get is a sort of X-shaped figure on our space-time diagram, and we've agreed that any line that is steeper can be traversed by us, and any line that's shallower cannot. That means that the upper triangular region of the space-time diagram is areas that we can travel to, and the lower triangular region of this space-time diagram is areas that we can travel from. So these create structures called light cones. So we have one light cone at the top here and one light cone at the bottom. We have proper names for these. So the one at the bottom is called the past light cone, and this encompasses every single possible event that could have had a causal influence on our current space-time coordinates. What this is basically saying is that if there's any event that ever affected our current position or our current circumstance, it falls within this yellow triangle. If there was an event outside this yellow triangle but still before us, before our current space-time coordinates, it couldn't have affected us because information, it would have to travel faster than light for information from it to reach us. So yeah, this includes all transmitted signals, any rays of light which would have followed the light-like world lines on the edge, and even spacecraft. And similar to the past light cone, we have a future light cone. And the future light cone encompasses every single event that we can exert a causal influence on, which means if I wanted to travel to a point anywhere in space-time, I am restricted to only this future light cone. I cannot travel to a different set of space-time coordinates, simply because it would require me to travel faster than light and would break causality. Again, this includes any signals I've transmitted, any beams of light I've shot out into space, or any rockets that I've launched. Now, you'll notice we have more than half the diagram sort of unavailable to us, and this sort of elsewhere region is causally disconnected from our space-time coordinates, which means any event that lies within this purple region cannot affect us, and we cannot affect any region and any event within this purple region. There is no frame of reference in which these events can have a definite time order. And what we mean by that is, if I have, let's say we have an event in the upper right-hand corner of the unavailable area of the space-time diagram, and we have another event in the lower right-hand corner, we can't tell which event would have happened first, because relative to another event, let's say on the left side, one of these events could be in the future light cone for that observer, but could also be in the past light cone for another observer. And this basically represents how we're causally disconnected from half of this space-time diagram. This also enforces the law of cause and effect, simply because the boundaries of the light cones are defined exclusively by the speed of light. So all these two x's, the x is formed by two light-like world lines, which are moving at the speed of light, and nothing with mass can travel at this speed, as we already know, but it can only approach that speed. So the way this enforces the law of cause and effect is that effects cannot precede their causes. I'll talk a bit more about this during the presentation, but the general idea is that this is the reason the universe makes logical sense, because again, effects cannot precede their causes. When we talk about black holes, we're going to see how these light cones are manipulated and messed around with, and that gives us some really interesting mathematical features and effects that we haven't found observational evidence for yet. Okay, so let's just do a quick recap on how a black hole forms. Before that, I want us to just talk a bit more about space-time itself and how it curves relative to mass. So mass and energy determine the geometry of space-time, and you can find this through Einstein's field equations. And this curvature is what we perceive as gravity. So as you can see here, the larger the mass of this red object, the deeper the curvature of space-time. And the greater that, as you can see here, the greater the mass energy concentration, the more severe the curvature. Now, objects that are traveling, such as this yellow ball here, they follow what we call geodesics. These are the straightest possible paths in curved geometry. And another way to think about this is, if you look at a a plane's route on a flat world map, you'll often notice that the route is curved. But that's simply because the Earth is a globe. It's not a flat surface. And the fastest route connecting 2 points on a curved surface often ends up being a curved line when you project it onto a flatter surface. And it's this fundamental relation between matter and geometry that will set the stage for how we understand black holes as extreme manifestations of nature. Alright, so quick recap to how black holes form. Black holes form through the gravitational collapse of a massive star. So if the star is 30 times the mass of our sun, then it is likely to form a black hole. And when this star runs out of fuel and its core is full of iron, gravity takes over the radiation pressure in the star. So gravity begins to crush the core. As gravity begins to crush the core, all the empty space inside the atoms that make up the core is squeezed out, and the electrons and protons and neutrons are squeezed together until we form what we call a proto-neutron star. And this proto-neutron star isn't stable yet. It could still collapse further. And the only condition that it has for collapsing further is if that core exceeds the weight of 3 suns. So if the core is 3 times the mass of our sun, the core gravity will be strong enough such that the nuclear forces that are opposing its collapse will not be powerful, and gravity will continue to shrink the core until a black hole is formed. So another way of looking at this limit is it's called the Oppenheimer-Volkoff limit, and it's the maximum mass a neutron star can have before it collapses into a black hole. Alright, so now that we know how black holes form, let's talk a bit about the most familiar feature of black holes, which is the event horizon. So this event horizon is called a null surface, and it acts as a causal boundary. I'll talk about what a causal boundary is in a bit, but a null surface is simply a surface that isn't something you can touch or feel or experience. It is a surface demarcated by, in this case, a photon, such that if you were to place a photon at the event horizon, it would actually orbit the black hole. And mathematically speaking, the event horizon is defined by the Schwarzschild radius, and the Schwarzschild radius is proportional to the mass of the neutron star, or the black hole. So in this case, g is the gravitational constant, and c is the speed of light. So it simply depends on how big the black hole is. And at the horizon, we define another quantity as well, and this is called the surface gravity. This simply measures how strongly the horizon pulls the nearby space-time around, and hence the nearby geodesics. And it is inversely proportional to mass, which means smaller black holes will curve space-time a lot more, and they'll pull a lot more, but larger black holes in size will have gentler, softer event horizons. Now, as we all know, if you were to fall into a black hole, a distant observer will only see you approach the black hole and then slow down as you near the event horizon, and eventually turn red and redder and redder and redder until you fade away. This is called the infinite redshift effect, and that's pretty much what a distant observer would see if you fell into a black hole. Here is a video of us falling into a black hole. I don't think it's playing. No worries. So basically, if we were to fall into a black hole, we know what we would do from the distant observer's point of view. But what if we were falling into a black hole? So far away from the black hole, everything seems normal. We don't notice any extra gravity. We don't notice anything weird with our clocks. But as we start to approach the horizon, we will notice that the strength of gravity continues to increase, and our future light cone will actually start to bend in towards the black hole. To an observer watching from far away, like we said, it looks like we're slowing down and fading out. But for us, we don't notice any change in our clocks. We don't notice any change in the strength. I mean, we don't feel like we're being tugged in one direction. For those that have watched Interstellar, you will remember that when Cooper was orbiting Gargantua and was on Miller's planet, he didn't know that time was passing much faster. He couldn't experience that time passing much faster. Inside the black hole, however, once you cross the event horizon, you won't notice that you've crossed the horizon because, again, it's a null surface. But once you cross the event horizon, everything flips. So time becomes space, and space becomes time, in the sense that the way we can't stop the flow of time, forward flow of time, such that we can't stop tomorrow from happening, inside a black hole, you can't stop yourself from going towards the singularity. It's not a place in time. It's not a point in time. It's just something you're moving towards. Okay, so now that we've talked about black holes and how they form, let's talk a bit more about how we can represent this sort of bizarreness of an event horizon and of infinity on paper. So I want to take you back to the problem with traditional diagrams. If you were to look at any map of the Earth, you will always find some sort of distortion. And that's simply because standard standard diagrams of the globe cannot properly project a globe-like surface onto a flat surface. So you'll see there's different types of world maps that exist, but each one has its own flaws. Similarly, we have space-time diagrams that have two major flaws in them. The first one is you cannot see infinity. If you remember the space-time diagram I showed you earlier, you could see that it only shows a range on a given axis as far as you want it to. It can't show infinity. And the diagram's edges, again, are arbitrary. And secondly, these things break down at the horizon. So the equations for Schwarzschild coordinates break down at the event horizon and they become meaningless. And I'll talk more about how that happens. But the general idea is standard space-time diagrams cannot help us understand black holes and extreme limits like event horizons as well as we want to. So the solution is simple. We switch to a compactified space-time diagram, and this is what it looks like. We've got our regular grid, and what we do now is we conform it to a new sort of diamond-like shape, and what we get is a Penrose diagram. So the Penrose diagram is more than just the diamond I showed you, but this diamond represents region 1 of the Penrose diagram. Now what is region 1 of the Penrose diagram? The region 1 of the Penrose diagram is simply the entire universe. What we've basically done is compressed the entire universe into one diamond, and this diamond isn't a linear diamond in the sense that the bottom edge of the diamond represents infinite past, the top edge represents infinite future, and the right edge represents infinite distance. If you look at these vertical purple lines, they represent specific points in space, and if you look at the horizontal lines, they represent specific points in time. Now, this space-time region is almost flat. It approaches flat. We call it asymptotically flat. Simply because there's always the gravitational influence of a black hole next to it, and no matter how far you get away from it, the black hole will still exert some sort of gravitational influence on you, so space-time can never be truly flat. Now, one thing this diagram does for us in this region is it makes causality global. Now, our light cone method still applies here. I can plot a point right here where I have an event going on, and I have another event in a different part of this diamond, and you can draw light cones from one to another and check if they are causally connected or disconnected, and if one falls in the future cone of another or not. Now let's move to the black hole. The black hole is represented by region 2 of the of the Penrose diagram, and this is this triangular figure over here. The border between region 1 and region 2 is the event horizon, and it's at the Schwarzschild radius. Now, like I said, the purple lines represent distance, so further out you get from r equals 2m, you can go further out, you get r equals 4m, and it keeps going towards the right hand side until you get to r equals infinity. Inside the black hole, like we said, you cannot escape when you enter a black hole. So if I were to plot a point anywhere inside that triangle and draw a future light cone from there, you would still be inside the black hole, and that further demonstrates the fact that you cannot escape a black hole once you enter it. The singularity is the line up here which says r equals 0, because that's where we're measured, that's where the diagram is that's the limit. Now, let's talk about white holes. If I were to plot a light cone from this point where the rocket is, you'll notice that our future light cone is in the black hole, but we also have a past light cone. So that region becomes a white hole, because anything that exits it can causally affect us, but we cannot go back in time to that point. So now this becomes region 3 of the Penrose diagram, and this is the white hole region. The white hole region is a polar opposite of a black hole. Instead of a future singularity and a future event horizon, you have a past singularity and a past event horizon also at r equals 0. And this, like I said, is region 3. So unfortunately, we haven't observed a white hole yet. We haven't confirmed that it exists. It is purely hypothetical as of now, but I will talk a bit more about white holes as well. All right, so you can exit the white hole on the left or the right, and you can enter the black hole from either the right or the left. What that means is, on the other side of the black hole and white hole, you have another set of space-time coordinates. Basically, what that means is, we have another set of a universe, basically, simply because if I were to plot any point inside the region 1 of space-time and draw a future and past light cone, there is no combination, there's no point in our universe that has a future light cone or past light cone that covers any part of region 4 of the Penrose diagram, which is our parallel universe. Therefore, this set of space-time coordinates is causally disconnected from our set of space-time coordinates, and what that means is that this is a parallel universe. Now you'll notice there's a point where where these event horizons converge, and our universe sort of touches the parallel universe. This is called the Einstein-Rosen bridge and has some very interesting mathematical properties that I will talk about in just a bit. Okay, so a quick recap on what we did. We talked about the Penrose diagram. We also talked about how black holes are plotted on the Penrose diagram, and we also talked about the possibility of white holes. But one caveat I forgot to mention was that all these objects we talked about are not spinning. So the black hole in this case is perfect, has no angular momentum. The white hole has no angular momentum. But there's a bit of a problem with that, because in real life, stars spin, stars rotate about their own axis, and since stars are what form black holes, therefore angular momentum is conserved, and once the star dies and forms a black hole, the black hole must also spin. So for all black holes that don't spin, we use what we call the Schwarzschild solution. And we want to now generalize to black holes that have a spin. And this is because rotation will significantly alter the black hole's geometry, and it leads to a lot more fascinating features. So instead of the Schwarzschild solution, we now use the Kerr solution to Einstein's equations. And the Kerr solution is more general, and we can use the Kerr solution to get the Schwarzschild solution as well. Let's talk about it. So, in the Kerr solution, the black hole is no longer a perfect sphere. It now becomes an oblate shape because it bulges at the equator because of how it spins. Now, the black hole generates two distinct horizons instead of one. So with the Schwarzschild solution, you have the event horizon and then you have the singularity. But with the Kerr solution black hole, you have an inner horizon, you have an outer horizon, and you also have this weird region just inside the outer shell called the ergosphere. And inside the ergosphere, space-time is being dragged so fast that you have this effect called frame dragging. Now, frame dragging is basically a process where where space-time spins faster than the speed of light. Now, an important distinction needs to be made, such that just because space-time spins faster than light, it doesn't mean that you cannot escape this region. The ergosphere is a region of a spinning black hole that you still can escape if you have a clever enough trajectory, but you can never remain stationary inside the ergosphere. No matter how hard you try, even light cannot remain stationary inside the ergosphere. And this gives us a very interesting theory where we can use the properties of frame dragging to make the Penrose process possible. The Penrose process is a clever way to try and mine, it's hypothetical obviously, but it's a clever way to try and mine the rotational energy of the black hole that we can experience in the ergosphere. What it effectively does is it splits a particle, and it lets one of the particles go into the black hole, so inside the outer horizon and inside the inner horizon towards the singularity, and it lets as a result, the second part of the particle, will be ejected from the ergosphere, and it will have more energy than the original particle. So what we've done is we've sort of mined some of the rotational energy of the black hole and transferred it to this particle that we split so that it could escape the ergosphere. Now, if we move towards this boundary that we see in here, this sort of oblate shape, this is the outer horizon. Remember, the outer horizon, just like every other horizon, is a null surface, which means it's not a surface like this that you can see or touch or experience. It's just a limit that once you cross, you cannot return. For an outside observer, again, similar to a Schwarzschild black hole, any inward falling object appears to freeze and then turn red as it fades away. Now, mathematically speaking, to find the radius of the outer horizon of a spinning black hole, you have this equation. Now, unlike the Schwarzschild black hole, which only depended on the mass of the black hole, we also have the letter A here. And the letter A here defines the spin parameter of the black hole. Now, the spin parameter is dependent on the angular momentum. So this letter A simply is a value that communicates how fast the black hole is spinning. And even though an outside observer cannot tell the difference, even though an outside observer can see the difference where we fade away and redshift, for a person falling into the black hole like we are right now, we will notice no difference. We won't feel like we've crossed a surface or crossed a limit. For us, we're just falling into a black hole. Now, moving up from the outer horizon, we move to the inner horizon. Now, the inner horizon is where things get really, really, really weird. Firstly, the value defining the inner horizon is this equation, and the only difference between the outer and inner horizon is this minus before the square root is a plus for the outer horizon, and it's a minus for the inner horizon. Now, inside the inner horizon, things get very weird, because any radiation or matter falling inside the black hole becomes infinitely blue shifted instead of red shifted. And inside the horizon, the future can no longer be uniquely determined by initial data. Basically what we're saying is time loops. So the past will happen again inside the inner horizon. It is also possible for there to be certain paths through space-time inside the inner horizon that loop back to their own past, and these lead to causality paradoxes such as the very famous grandfather paradox. Now, in practice, the inner horizon cannot exist stably because it needs a very specific set of conditions, and any disturbance tends to cause it to collapse into the singularity itself. Now let's just do some horizon math. You'll notice I mentioned that the outer and inner horizons are defined by pretty much the same equation, and whether you want the outer or inner horizon value depends on whether you put a plus or a minus before the square root. Now, I mentioned earlier that you can use the Kerr solution to get the Schwarzschild solution again. So what is a Schwarzschild black hole? It's a black hole that doesn't spin. And if it doesn't spin, the spin parameter A is 0. So if you set the spin parameter A to 0 in the second equation on this side, you'll notice that this square root sort of drops because it cancels with the square. And based on whether you're calculating the outer or inner horizon, you get these values. The outer horizon becomes 2gm over c squared, and the inner horizon becomes 0, which is the exact values for the Schwarzschild case, because there is no inner horizon for a Schwarzschild case. You have only one horizon. But there's a second specific value of A that you can set to make this square root disappear. And that value is gm over c squared. Because if you were to set A to the same value as the other component here, under the square root, the entire square root evaluates to 0. And what you have is the outer horizon is equal to the inner horizon, and they're at the same limit. And this is called the extremal Kerr case. Now, just a quick review. In the Schwarzschild case, you cross the one and only horizon, which is technically the outer horizon, and inside, time and space shift, and you have red shifting as you enter it, normal stuff. For a regular Kerr solution, before you enter the outer horizon, a distant observer watches you redshift. When you enter the outer horizon, normal, but when you enter the inner horizon, things become much, much weirder. But for the extremal Kerr case, because the outer and inner horizon are the same, it's almost like you're not entering the outer horizon, you're directly jumping to the inner horizon. So instead of experiencing the regular black hole stuff we would have studied, you go straight to the very, very weird stuff. So that's why it's called the extremal Kerr case. Now, we can go inside the inner horizon, obviously, and The Schwarzschild singularity, for a black hole that doesn't spin, the singularity is 1 point. But for a Kerr black hole, the singularity is no longer a point, it's a ring. And it's a ring that's equatorial in nature, so it's along the equator of the black hole. And the radius of this ring, again, is proportional or is defined by the spin parameter A. So again, if I had a black hole that wasn't spinning, that radius would be set to 0, aka a point singularity. Now, pure Kerr math, aka an ideal solution where an ideal scenario where you have no disturbances, no instabilities, would allow for this. And what it would allow you to do is sort of hula hoop through this ring. So you could go through this ring, and it leads to even weirder events with the Penrose diagram, where you have multitudes of universes you can enter, and it sort of becomes just a door to all this craziness. But in practice, there's tons of tidal forces, there's tons of instabilities that would exert a force on the singularity, and as a result, this wouldn't happen. You wouldn't be able to loop through the singularity. In fact, this entire region would sort of be a point singularity. Great, now that we've sort of turned our brains into spaghetti with black holes that spin, let's talk about the exact opposite of black holes, and that is white holes. Now, if you remember, white holes occupy region 3 of the Penrose diagram. These are, the way you obtain a white hole solution from a black hole solution is simply inverse time. So any value for time in a black hole solution, you replace with minus t, and you get a white hole solution, because instead of stuff entering, now stuff is leaving the event horizon. And what this does, it highlights the temporal symmetry in general relativity, because you can inverse time. And mathematically speaking, this means that there is nothing preventing a white hole from actually existing. But obviously we have no observational evidence to this day of white holes. Now, let's talk about their causal structure. You remember I mentioned that with black holes you can enter but you can't leave, and you will be forced towards the point singularity. In the case of white holes, firstly, they're causally disconnected from most of the universe, and this can be easily seen if you put up the Penrose diagram and start drawing light cones everywhere. And also, with a white hole, any matter or signal inside the white hole must move outward. That's something you cannot prevent, cannot stop, and no external influence can affect the inside of the white hole. This defines a one-way causal boundary. Again, what is a causal boundary? A causal boundary is simply a one-way route. For a black hole, the causal boundary is such that you cannot come back, and in this case, the causal boundary is something you cannot enter. It's a perfect opposite of a black hole. And instead of a future singularity, we have a past singularity. So that singularity expels matter instead of assimilating it. Now, in theory, white holes emit matter and energy in the forms of high energy particle streams, in the form of radiation bursts, or in the form of plasma ejections. Now, this emission is obviously a direct consequence of the past horizon structure, but that energy outflow is, in theory, highly unstable. And what that means is white holes can only exist briefly if you look at the math. Let's talk about some more reasons why white holes cannot exist. So unlike black holes increase the entropy, local entropy, but white holes will emit low entropy matter by nature. What that means is it will reduce local entropy, and that violates the second law of thermodynamics. And that also contradicts the observed arrow of time. And similar to that, white holes appear unphysical as persistent astrophysical objects. So even though they're valid mathematical solutions, it's not something you would expect to see in the real universe. Let's also talk about how a white hole would form. We know how a black hole would form. A black hole forms through stellar evolution, but white holes are not formed through the same process. To form a white hole, you'd need extremely fine-tuned conditions, and you'd need a geometry in space-time, and that sort of geometry is exotic and unstable, not necessarily naturally occurring. And obviously, similar to the Kerr solution, any further disturbance such as incoming matter or radiation will destabilize the white hole, and one of two things can occur. A, the white hole just disperses entirely, or B, the white hole transforms into a black hole. Now, the sort of fine-eyed amongst you might have noticed that if a white hole's job is only to expel matter, and the only other cosmic event we know that expelled a ton of matter and energy was the Big Bang. There are speculations that the Big Bang could be similar to a white hole, but the reason it's not possible is because the universe didn't exist before the Big Bang, and a white hole would expel matter into a universe. So without a universe, you can't necessarily have a white hole. So the Big Bang is not a white hole. Great. Let's now talk about the little point of contact we saw between our universe and the parallel universe in the Penrose diagram. I told you this was an Einstein-Rosen bridge, and it has some very interesting properties. Firstly, an Einstein-Rosen bridge is also known as a wormhole. We all know about this simply as an interstellar highway. You can enter through one side, you leave through the other side, and you've basically traversed at any given distance in a much shorter time. Now, formally speaking, again, the Schwarzschild metric, it talks about a black hole that doesn't rotate. So again, for now, this solution is about a black hole that doesn't rotate. And a wormhole is not something we can cross, unlike what movies have led us to believe. And let me tell you why. So, in the Schwarzschild case, where a black hole doesn't rotate, as you can see in this animation, the wormhole collapses instantly because the singularity is at the center and it pulls in space-time until it pinches it off, and the wormhole's pinched off such that any particle that's trying to cross will hit the singularity. The speed at which the singularity pinches the wormhole is the speed of light, therefore even a photon couldn't cross through in time. Now, if you were to toss anything into a wormhole by chance, it would only accelerate the gravitational collapse because remember, you're adding more mass to the singularity. These wormholes, though, are mathematical features of general relativity, and all they do is illustrate the topology of space-time. They also illustrate the limitations that we have with classical horizons and classical physics, and they also talk about the potential intersections of quantum mechanics and relativity. And what I basically mean by that is quantum entanglement is thought. There are theories that suggest that quantum entanglement could be linked to microscopic wormholes that link both particles regardless of where they are in the universe. Okay, let's say we wanted to traverse a wormhole. We know that we can't traverse it, but what if we wanted to try? So, like I said, the problem with the wormhole is that it's pinched shut too quickly for us to cross in time. So, the way to solve that is have something opposing that pinching force. So, what we need there is to reduce the power of the singularity. And to reduce the power of the singularity, you need exotic matter. By exotic matter, we just mean something that has a negative energy density and a negative pressure, because it would oppose the collapse of the pinching off of this wormhole. Now, the amount of exotic matter you would need is way beyond our current technology and definitely does not exist in nature. So whilst traversing a wormhole remains speculative, we don't have any known stable solutions where we could cross a wormhole. Now let's talk about a wormhole that rotates. Remember, we don't use the Schwarzschild solution for most astrophysical black holes because most real black holes have a spin parameter. Now, if we were to generalize the Schwarzschild solution to obtain a Kerr solution, you could have rotating ER bridges. So obviously this animation is for a Schwarzschild black hole, but you could see it rotate. Now, rotating wormholes are obviously mathematically richer because now not only do you have to look at the pinching, you can also look at other stuff like how fast it spins, the relative spin between one of the mouths versus the other, but it doesn't change the fact that you cannot cross a wormhole without the use of exotic matter. Now, as a result, obviously, all time-like and light-like geodesics that enter the throat converge to the singularity. What this one line is basically saying is, time-like geodesics are any path that you can take through space-time that is slower than the speed of light. Light-like geodesics are any path you can take through space-time that is at the speed of light. And the only other type of geodesic we have is a space-like geodesic. A space-like geodesic, like I said, is a path through space-time that goes faster than the speed of light. And obviously, if you could travel faster than the speed of light, you could cross the wormhole before it's pinched shut. Therefore, only the time-like and light-like paths converge to the singularity, as opposed to emerging on the other end. Now, let's talk about how quantum mechanics is potentially linked to wormholes. We have a conjecture. A conjecture is simply a theory that hasn't been proven or disproven. And this conjecture says that quantum mechanics, or rather quantum entanglement, is linked to wormholes. It's called the ER equals EPR conjecture, where ER is Einstein-Rosen bridges, aka wormholes, and EPR is Einstein-Podolsky-Rosen, which is quantum entanglement. Now, this has a few implications. If this is true, this has a few implications. Firstly, quantum entanglement could be interpreted geometrically, because we can describe a wormhole geometrically, and therefore we would be able to describe quantum entanglement geometrically. Secondly, it could provide a path for us to resolve the black hole information paradox. The black hole information paradox is basically something that says that information is lost when something enters a black hole, but information shouldn't be lost. Therefore, there are different ideas that information could exit via tiny wormholes within connecting the black hole to the outside, or again, very weird physics. The third thing this suggests is that there's a profound unity between quantum mechanics and the geometry of space-time. Great, now that we've looked at black holes, we've looked at spinning black holes, we've looked at white holes, and we've also looked at Einstein-Rosen bridges. Let's now talk about time. You will remember at the beginning of this talk, I mentioned that there are possibilities for time to loop back in itself, where you can experience your own past again. We call this a closed time-like curve. Time-like again because we are moving slower than the speed of light, yet it's a closed curve, therefore we experience the same space-time coordinates, aka the same time and place again. Now, locally, the way these work is locally the traveler experiences time normally. So for them, they're moving forward through time, they're probably going about their day, doing normal stuff. But globally, in the entire system, their path circles back and their future reconnects with their past. A good analogy of this is trying to circumnavigate the globe. Let's say I'm in Cape Town and I'm walking northbound. If I were to walk in the direction of north, locally I'm walking straight and I'm only walking straight. But eventually, if I circumnavigate the entire globe, I will end up where I started. I'll end up in Cape Town. And that's basically what's happening here, except it's not just space, it's also time. Now, these time-like curves can form in a few environments. Inside the inner horizon of a curved black hole. They can also form inside a rotating cosmos, where space-time itself is rotating. They could also form inside the mouth of a wormhole. Now, for that to happen, you have one mouth spinning faster than the other, and the speed difference between them, if it's great enough, could lead to a closed time-like curve. Now, a closed time-like curve basically illustrates the idea of time travel. And if we're trying to say that these might be possible, we have to face every single time travel related paradox that we've come up with so far. Here are a few of them listed. Firstly, we have the grandfather paradox, where you can alter your past self's existence by interfering with your ancestry. The second paradox is the bootstrap paradox, where information or objects are trapped in a loop without origin. For instance, let's say I took Shakespeare and I time traveled back to that era, I gave it to him, and then he publishes it, he becomes famous, and once he becomes famous, I buy a copy, I time travel back, and I give it to him. This sort of paradox leads to us questioning who the real author of Shakespeare becomes. That's the bootstrap paradox. And obviously, we have a collapse of causality, because now you can no longer differentiate between what is the effect and what is the cause for a certain event in space-time. And the effect can be its own cause. Now, the principle we have here to sort of govern all this madness is called the Novikov self-consistency principle. The principle simply states that if closed time-like curves exist, paradoxes cannot exist. And how does the universe enforce that? Well, it enforces it by editing events to maintain self-consistency. Let's say I wanted to hand Shakespeare to Shakespeare himself. Maybe the boat I would use gets delayed. Maybe the boat sinks. Maybe I don't get to meet Shakespeare. Maybe he's too busy. Maybe the store I go to buy Shakespeare before I time travel is out of stock. But the universe will edit events to make sure that it's self-consistent. Now, this has an implication if you shift your perspective. That implication being that your initial conditions aren't fully free. Let's say that store is out of stock and will always be out of stock of Shakespeare, and I can't buy Shakespeare. Basically, what the universe has done is it's limited what I can do. It's limited my own free will. And whilst it preserves consistency, it shifts our notion of free will, because locally speaking, you're free to act. I could drive to the nearest bookstore. I could drive to Johannesburg to see if Exclusive Books has Shakespeare there. But I am, globally speaking, still locked in the same loop where I will not be able to buy Shakespeare, or I won't be able to give him Shakespeare. I cannot break the consistency enforced here. In other words, what I'm trying to say is, if closed time-like curves exist, you do not have power over your past will have power over you. So you are no longer free to do anything. The universe has locked down the options that you have for things that you can do. Okay, some more spaghetti later. Let's now delve into some math-related or more mathematical ideas, where we talk about how these limits, these extreme limits, affect the equations that we have, and how these equations very beautifully portray extremes such as the event horizon or singularity. So, quick revision of the singularity. According to general relativity, the curvature of space-time is measured by quantities like the specific scalar, and the heavier the mass, the more curvature. At the center of a singularity, for a black hole that's not spinning, this scalar becomes infinity. And another thing that becomes infinity is your volume. How? Because a singularity compresses all of its mass into zero volume, and therefore density equals mass over volume, and mass over zero blows up to infinity. Inside the event horizon, space-time flips because the radial coordinate r, which is a funny way of saying how far you are, how big your radius is away from the black hole, from the singularity, that becomes time-like, and your time coordinate becomes space-like. Basically, that radius continues to decrease, that r will continue to decrease to zero because you're going to eventually hit the singularity, but you can change your time coordinate t. Now, every time-like and light-like path, again, time-like is slower than the speed of light, light-like is the speed of light, and inside the horizon, they will approach zero. Like I just said, the radius will approach zero as your local time tau increases. The symbol is tau. Let's talk about the field equation. I've been talking about the field equation a lot, but I've not shown you what the field equation is. This is Einstein's field equation. Obviously, I wouldn't be surprised if you wouldn't recognize a lot of these variables, so I'm just going to quickly run you through them. The first variable we have here is called the Einstein tensor. This is a clever combination of a tensor and another scalar multiplied by a tensor to ensure that the laws of conservation of energy, the laws of conservation of momentum, and all of these conservation laws hold. This, you can see there's two equal signs here, but that's simply because the Einstein tensor is often used to substitute the second expression you can see in this equation. Speaking of the second expression, the first variable in the second expression is the Ricci curvature tensor. And what this tensor does is describes and measures how much space-time is curved locally by matter. Again, the more mass the matter has, the more space-time curves. And this tensor describes how much that space-time curves. We have a scalar in the second part of the expression, r, and this represents the overall curvature at a single point in space-time. And that's why it's a scalar, because it's one value as opposed to a tensor of values. But the scalar is attached to a metric tensor, and this metric tensor encodes the geometry of space-time, including the lengths, the angles, the intervals. So if you were to think of space-time as a flat grid, this metric tensor would encode that geometry within it. So you can see the left side of this equation is very geometry related, but the right side of this equation is very physics related. You have the stress energy tensor, which is the only variable in this side of this equation. It describes matter, energy, and momentum, and also describes stresses and pressures. And it's multiplied by a constant, which we call a coupling constant, and this coupling constant consists of 8 pi g over c to the 4. G is the gravitational constant, and c is the speed of light. Now, why did I just show you the field equation? Simply because this field equation predicts its own breakdown as you're approaching a singularity, and that's what's so beautiful about it. The right side of this equation, like I mentioned, is the physics side. It details the energy and momentum of matters and fields, and the left side is the geometry side, which details the curvature of space-time, how space-time curves, and stuff like that. Near singularities, solutions using the field equation yield infinities. They blow up to infinity, and this basically means the equation is saying, I don't have a prediction at this specific point in space-time. It doesn't say that it collapsed on its own. It predicts that it collapsed because it says that singularities aren't avoidable artifacts, but they are built into the structure of relativity. It's not saying it's beyond a certain scope of the equation. It's saying it's part of the equation, and it's saying that it cannot predict a value, or it's not valid at these points in space-time. Now, let's talk a bit about quantum fluctuations. This is extremely interesting. So the general basis for this idea is that in quantum field theory, even empty space has energy. It has particles, and a phenomenon that we witness is that particle and antiparticle pairs can constantly appear and annihilate as long as they do so within a specified time delta t. So that's the lifetime of the fluctuation. As long as this inequality holds, where the energy and the lifetime of the fluctuation are greater than h with this cross through it. H with this cross through it is basically the reduced Planck constant. That's h divided by 2 pi. And as long as you obey this inequality, particle-antiparticle pairs can appear and disappear out of in the vacuum of space. They need nothing to trigger them. They constantly do that. Now, if you do this close enough to a black hole, these particle-antiparticle pairs will still continue to form and annihilate, but you could have an instance where once the particle-antiparticle pair has formed, either the particle or the antiparticle could be sucked into the black hole, whilst the other stays out of the black hole. Now, when this delta t, this time delta t expires, that means that we won't have both particles to annihilate each other. One of the particles will still continue to exist. This is what we call Hawking radiation, and the loss rate for Hawking radiation for a given black hole is inversely dependent to its mass. So the smaller a black hole is, the faster it evaporates. Now, it's also linked to thermal energy because this emitted radiation is thermal in nature, and the temperature is inversely proportional, as you can see in this equation. So the temperature, the Hawking temperature, the radiation temperature, is inversely proportional to the mass. So the smaller the black hole, the higher the temperature of the emitted radiation, and the faster it evaporates. Over here you can see an animation. We have a circle representing a black hole, and you have these blue and red particle-antiparticle pairs forming. Now, one forms too close to a black hole, and the red particle gets swallowed, and the blue particle doesn't get annihilated, so now it's free to go. So we've basically got a particle for free at the expense of the black hole. Okay, so what have we learned from today's talk? Well, the entire idea behind today's talk was to help you visualize infinity. Infinity is a concept we, as humans, cannot comprehend very easily, but with tools such as the Penrose diagram, with tools such as Einstein's field equations, and stuff like that, we can understand infinity. And by understanding infinity, we also have side effects where we can understand and discover new objects or regions of space-time. We have the interior of black holes, which we've never visited. We have the interior of white holes, which we've never visited. And we have the hypothetical landscape that parallel universes exist. It also lets us see the global structure of causality. We can take our Penrose diagram, region 1 of our Penrose diagram. We can plot any 2 points, and we can check if they are causally connected, regardless of how far they are in space-time, apart from each other. Out of all of this that we've seen, obviously our universe, we are in our universe, so we've confirmed that through observational evidence. And black holes and event horizons also, we've confirmed through observational evidence. However, white holes, wormholes, and parallel universes still remain hypothetical because we haven't seen them in real life. And again, the general crucifix of this talk is that singularities and infinities are not ultimate boundaries. They are just frontiers that we can still cross, provided we have the right tools. Thank you so much for listening to me. Do we have any questions? Do we have any questions?
Yes,
Ask a
Jared.
question.
Yes, Jared.
So it's David.
Yes, David. What's your question, David?
Oh, sorry. I'd just like to say well done to Archel. It was a great talk with wonderful illustrations. I was just wondering, you mentioned the Hawking radiation at the end. Is there anything comparable with white holes to Hawking radiation?
I would imagine that there would be an analogous sort of idea related to white holes as well, but I would imagine that would be difficult to discern simply because Hawking radiation's general idea is that a particle is absorbed, but white holes emit particles. So even if a particle-antiparticle pair formed outside the white hole, it would just be pushed away. But I would imagine there is some geometry in which we can find something similar to Hawking radiation, but for a white hole.
Thank you.
I see a question in chat. It says, are we looking at black holes from a scientific, cultural, religious, philosophical, artistic, or psychological perspective? Do we use math theories like field theory and spectral theory to understand black holes? And do we use complex analysis to analyze black holes? This talk was mostly from a scientific/mathematical perspective. And yes, theories like the field equations and diagrams like the Penrose diagrams are extremely useful in understanding black holes and analyzing black holes as well, because we can confirm our own theories with observational evidence and obviously see how it scales with different types of black holes, whether they're spinning or not, whether they're two black holes merging with each other or not, and things like that, yeah. We have another question. Are there size ranges for wormholes, such as supermassive wormholes or miniature wormholes? Do we use tensor calculus and use differentiation for the 4D Schrödinger equation? Do we use Newtonian, Helmholtzian, Lagrangian mechanisms to understand wormholes? Okay, so Einstein's field equation in and of itself is a differential equation, and I would imagine differentiation, obviously calculus is a huge part of all of this. In terms of size ranges for wormholes, yes, definitely there are size ranges for wormholes, because remember, wormholes are linked, well, they are the link between one universe and another, and that link forms at the event horizon of both a white hole and a black hole. So as a result, if the white hole / black hole has a different size, then that would lead to the wormhole itself having a different size. And yeah, since we have supermassive black holes, if wormholes do exist, I don't see why we can't have smaller wormholes and bigger wormholes.
Acha, you mentioned at the start of your presentation that the minimum mass of a star should be around about 3 times the mass of our sun in order that it evolves into a black hole. How did we arrive at that minimum mass?
I believe it was calculated. Um, the yeah, I do believe it was calculated because at that it's basically the limit where the force of gravity becomes stronger than the nuclear force that's being exerted by these
Okay,
protons and neutrons within the atom.
okay. Your vast knowledge of astronomy, how do you eventually intend it to link with your mechatronics?
Okay, so the entire reason I chose to do mechatronics engineering was so that hopefully I could help with the engineering side of um, astronomy, because obviously when you think about telescopes like James Webb Space Telescope and Hubble Space Telescope, most of them are described as feats of engineering. And for astronomers and humanity as a species to be able to observe that far back into the past using JWST, for instance, it took a team of engineers to, you know, sort of go out of their comfort zone and build something that the world's never seen before. So that's why I'm doing engineering, because I that's how I want to merge my love for space and engineering together by basically
Wonderful,
building the tools that astronomers can use to explore space.
wonderful. Yeah, that's very good. Yeah. You mentioned the parallel universe. Is that the same as multiverse?
Yes, so in the case of the Penrose diagram, the parallel universe could either be within our universe or it could also be in a different universe. The only criteria is that these two sets of space-time coordinates have to be disconnected. Now, when I mentioned Kerr black holes, if we were able to loop through the singularity, we would most certainly enter multiverses, because now the Penrose diagram would basically sort of lift up and um, expand, and the Penrose diagram would then become stackable in a sense.
I think there's another question. Aman, can you simulate a wormhole on a computer?
Okay, so yes, in theory you can simulate a wormhole, but it would be extremely difficult. So during the filming of the movie Interstellar, the black hole shot there, Christopher Nolan wanted a very, very accurate simulation of a black hole. It took, I believe, off the top of my head, I think it took 24,000 hours to render that entire black hole sequence for the movie Interstellar. And to this day, it is the most, I believe it's the most accurate simulation we have of a black hole. So if it took that long for a black hole, I can imagine it would take much, much longer for us to simulate a wormhole, because you'd have to simulate both the black hole, the white hole, and everything in between. There is another question. It's how useful is complex analysis in understanding black holes? I would imagine it's very useful. Black holes aren't my area of study, so I don't think I can accurately comment on that, but I would imagine that it would be very useful.